Hi, everyone. My name is Sandra Shah, and I'm pleased to be here today and honored to be a part of this project that is working hard to span local, Indigenous, and Western science knowledges and objectives. My role with this project was to coordinate a scoping review to take stock on what is known and what is not known relating to hydro impacts across dimensions, as well as to contribute a Western science perspective that would function to create a foundation for the research program. So welcome to our second knowledge sharing session. Today we'll have an expert panel on hydroelectric impacts across scales and social-ecological systems. And this is a part of a MITACS project with Grand Riverkeeper Labrador and St. Xavier University in Nova Scotia. So first and foremost, I'm joining you today from Corner Brook, Newfoundland, which is in the traditional Mi'kmaq territory. And this is where I'm currently living, working, and enjoying the beautiful land. I'd like to acknowledge with respect the diverse histories and cultures of the Beothuk, the Mi'kmaq, the Innu, and Inuit on this island, and I thank them. As an uninvited guest on this land, and a part of a legacy of violence and displacement, I continue my journey to unlearn and decentralize colonial thinking and action. In doing so, I hope to show respect to my neighbors, the First Peoples of this land, and I will continue to do my part in building back trust and strengthening relationships with them. So please feel free to introduce yourself in the chat. Let us know if you're okay with the Grand Riverkeepers contacting you. Let us know where you're from and what brought you here today, if you feel comfortable. So this recording includes a recap of the first knowledge sharing session, as well as all of the panelists' presentations that we'll hear today. I'll just briefly acknowledge the other project team members who shared welcoming remarks live at the event. But for the recording, I would just like to introduce Dr. Shelley Price from St. Francis Xavier University, our partner Roberta Benefil from Grand Riverkeeper Labrador, Karen Duela, an advisor from University of Victoria with deep ties to Grand Riverkeeper. Other advisors from Grenfell campus at Memorial University is Dr. Kelly Vodden and Brady Reed. Myself, as I mentioned, I'm Dr. Sandra Shah, currently a postdoc with Memorial University, and the project has also evolved from a key component that Nathaniel Bergbush conducted, and that is the scoping review. So again, just acknowledging that we have finished the original scoping review. We did knowledge sharing session 1, just an introduction to broad impacts from hydroelectric dams a few weeks ago. And today is our second session where we've brought in panelists to go deeper into these themes, specifically relating to coastal and marine ecosystems, fisheries, and livelihoods.
Last session, we just talked very broadly about the various impacts from hydroelectric development, the good and the bad, across all of these different dimensions. This overwhelming infographic talks about the key concepts that we noticed across time, across physical boundaries, and across these dimensions. So just a reminder from kind of that local scale around the infrastructure. We then took a couple steps back and looked at more of a regional view and what types of cumulative impacts can happen at the regional scale. This could occur from multiple hydro projects and in conjunction with other activities as well, and how they can combine synergistically, sometimes to create impacts, seen hundreds of thousands of kilometers downstream. And as Roberta mentioned, even affect global processes and services. And then we finished at the global scale, just again, acknowledging more briefly, because this is where we're really looking to our experts and connecting these dots for us. At each one of these scales, we got a really quick and broad introduction on what's out there with regards to Western science recorded impacts. And so that's what we want to do today, is really focus on the coastal and marine environment, downstream, and hear from the experts who are working on these types of projects. So let's continue the conversation and dive deeper into these types of impacts so we can better understand, implications to fisheries and livelihoods. So I'd like to welcome our expert panelists and get going on their brief presentations first. The format is each one of our guest speakers are going to provide up to a 10-minute presentation. Then we will invite any participants or team members to ask 1 or 2 questions if they want anything clarified, any terms, just any broad questions. And otherwise, after everybody's finished presenting, then we'll engage in a longer discussion with all of the panelists. So our first speaker, I'm very happy to welcome Dr. Taylor Mavara, and she is currently a Hutchinson Fellow in the School of Environment at Yale University. And Taylor's career has revolved around nutrient cycling, including carbon cycling of inland waters and global emissions from dams. So welcome, Taylor.
Yeah, thanks so much, Sandra. Oh, cool, you've got my slides there. So, okay, you're just going to advance them then? Okay. All right, well, yeah, I mean, thanks a lot so much for inviting me to this. And also, I'm just like so excited that folks are interested in hearing this, because I've, been researching this sort of thing for 10 years, and it's finally starting to kind of get out there into the world. And I'm probably as equally excited to be talking to you as it sounds like you are to hear from us. So yeah, I'm going to be talking about river dam impacts on nutrient cycles. And so Sandra, if you wanted to advance. Oh, too fast. Yeah, okay, so just to kind of give a bit of background in terms of nutrient cycles. So I study a few different nutrients. I study carbon, which is the basic building block of all life on Earth. And we tend to hear a lot about carbon in its gaseous form, so carbon dioxide and methane, because they're major greenhouse gases. And I'll talk about that a little bit in this little presentation. I also study nitrogen and phosphorus, which are also nutrients that are required by all life on Earth. And we tend to hear about nitrogen and phosphorus in water bodies when there's just way too much of them. And so we end up with these kind of algal bloom, or we call it eutrophication scenarios. And so I'll go into that a little bit more on the next slide. But I also wanted to mention nitrogen has a gaseous component, and nitrous oxide is another major greenhouse gas that can be tied to reservoirs. And I also look at a little bit at the nutrient silicon, which is necessary for lots of other species, mainly diatoms, which are basically the phytoplankton in coastal zones that represent kind of the most primary productivity on Earth. So they're super important, and they need silicon. So that'll come into play a little bit as well. Next slide. Yeah, so I mentioned some of the implications of having too much of these nutrients. And so basically we call that eutrophication. And so a classic example we hear a lot about in Canada is Lake Erie has a lot of nutrient loading and tends to experience eutrophication almost every spring. And so that arises either from high nutrient loading or kind of an upset balance of the nutrients. And so algae like to use nutrients in a certain ratio. And if you change the ratio of those nutrients, the algae that grow, or the communities of algae that grow, can be switched, and potentially sort of a more benign species can be replaced by a more harmful species. And so we'll talk a little bit about that in the context of damming as well. But basically, if you have this excess algae growth, you can end up with oxygen depletion, neurotoxin release, and fish kills. And so it's most of my research is global scale. And so Basically, eutrophication is something that's experienced by every coastal nation and nearly all nations on Earth with open freshwater bodies, and has a huge economic impact. So, like in the US where I live now, the impact is around $50 million annually. Yeah, next slide. Oh, I think went back still. Yeah, perfect. Was this one? Yeah. Okay. So I mentioned my research is mostly done at the global scale. And so this figure kind of just really summarizes the motivation for why I look at these trends at the really large scale. And so basically, this is a map or a map kind of summarizing a database of where the existing dams are, kind of the 7,000 largest dams in orange. And then in blue, the dams that are either planned or under construction. And so it's estimated that by the time these dams are done, more than 90% of the rivers on Earth are going to be severely fragmented by dams in some way. We're basically doubling the number of hydroelectric dams on Earth right now. So this is a huge impact to all rivers worldwide. Next slide. Oh, too far. This one, yeah. So this is really just sort of a simple primer of kind of the gist of what dams do to rivers. So before damming, you have a river, and kind of in terms of nutrients, what goes in is roughly equal to what goes out. But when you put in a dam, essentially you stop all this water, you create kind of a big reactor. And so you allow nutrients to start reacting and cycling around in the reservoir. And so one implication of that is you have burial of certain nutrients. And so this trapping of nutrients like phosphorus and nitrogen can result in these eutrophic cases in the reservoir itself. And then cycles like nitrogen and carbon that have these gaseous components, you can also have exchange with the atmosphere. So gas removal or gaseous emissions, and often in the form of greenhouse gas emissions. So I'm going to talk a lot about kind of the second half of this figure. Next slide. So yeah, we basically know that dams trap nutrients in their reservoirs, and this leads to all kinds of different responses in the reservoir as well as downstream. And so my research I'm going to give you sort of a primer on it, but it can be broken up into sort of 3 different categories. So I don't know if you can advance that to show the next few. Yeah, okay. So the first is, what's the impact upstream? And so basically, how much of each nutrient is trapped behind the dams? And does this lead to eutrophication or these harmful algal blooms in the reservoirs? The second is, what's the impact downstream? So do dams trap certain nutrients kind of more efficiently than others? And does this sort of upset the balance of these nutrient ratios delivered downstream and potentially changing the algal communities in the coastal zone? And if so, does this lead to these harmful algal blooms in coastal zones? And then the last one is, are dams really green? And so basically what I get at with my research in this is, do reservoirs emit greenhouse gas? Or, do dams help offset these greenhouse gas emissions by burying carbon and nitrogen in the reservoir? So I'll get to that. I'm kind of going to go through these one at a time and just give you a few snapshots of what I've looked at in my research. So let's go to the next slide. So I'm just going to start with upstream impacts. And so we can go to the next slide as well. Basically what I do is I build these computer models. I'm not going to go into kind of the detail of how I build them, but please, if you're interested, let me know. I'm happy to kind of walk you through them. But I built a few different models. So I'm giving kind of one example here where I predicted phosphorus trapping in reservoirs. And what I'm showing here is all the major watersheds on Earth and just how much phosphorus is trapped in all the reservoirs within that watershed. And so, for example, the Mississippi, I showed that almost half of all the phosphorus that ends up in the Mississippi River is buried in reservoirs, which is a massive, massive impact. And then I've shown a couple other hotspots. The Zambezi, even more than half of the phosphorus ends up in a reservoir. And so I built models like this for phosphorus, nitrogen, carbon, and silicon. And we ended up with kind of one big conclusion, which I think, Sandra, if you advance, it'll show up at the bottom. Yeah. So the big conclusion, which kind of almost wasn't even that surprising, is big dams and sequences of multiple dams are the most problematic to river system nutrient cycling. They trap the most nutrients in their reservoirs, and this can often lead to eutrophication with the possibility for harmful algal blooms. And we also showed that the possibility for these harmful algal blooms is the highest if there's already lots of disturbances upstream, like agriculture or wastewater treatment plants, where they're already loading lots of nutrients into the river that is then just all getting stopped by the dam and accumulating in the reservoir. All right, let's go to the next slide. So I'm going to talk about downstream impacts now. So again, we could just advance. So I mentioned I built a few of these models. And so Sandra, if you want this text to appear, that'd be cool too. And so basically what I found looking at the differences in nutrient kind of trapping for nitrogen, phosphorus, and silicon was that dams trap some nutrients more efficiently than others. And so they trap phosphorus kind of the most efficiently, followed by nitrogen and followed by silicon. And so I showed basically that sort of difference in how efficiently reservoirs trap these nutrients, combined with changes to how much nutrients are being loaded into streams already, can change what species thrive in coastal ecosystems. And so what I did was I took the output from all three of these models, and I looked at how the nutrient ratios are changing going to coastal shelves worldwide because of just the dams themselves. So I isolated the effects of the dams. So let's go to the next slide. And so what I show here is basically how the ratios are changing in terms of silicon. And so essentially, I mentioned diatoms earlier and how important they are for coastal ecosystems. And so diatoms need silicon. And so what I showed was that for year 2000, in a lot of parts of the world, damming might actually have helped coastal diatoms. And so essentially in this map, kind of the coastal shelves, if you see like a cool color, like a green or a blue, it means that the dams were changing the ratio to send more silicon to the coastal zones, potentially promoting diatom communities, which in general is kind of a good thing. But what I showed, this is a scenario we made for year 2050. We actually see that we might see a reversal of this trend. And so dam construction may actually hurt coastal diatoms communities around the world. And we see that basically this way more kind of silicon limited systems, which are indicated by this kind of hot or like red or orange colors. And without kind of getting into the details, it's sort of a complicated mechanism, but essentially boils down to differences in hydrodynamics of the new dams being built now compared to the ones from the last century. And so this potentially has major implications for coastal fisheries worldwide. Yeah, so let's go to the next slide. And then this last question, are dams green? And so really, this is something I'm getting into kind of a little more recently than the previous two topics. And I've mostly looked at the world of nitrous oxide. But I've my next slide, if we go to it, I basically summarize kind of the current state of the science in terms of whether dams are green. And I look at this mostly from the perspective of greenhouse gas emissions directly from the reservoir. And so it's really complicated. And in this particular regard, kind of at the global scale, it's still pretty uncertain. And so there's some reservoirs that clearly have larger greenhouse gas emissions per unit electricity generated than, for example, coal. But most of them, at least most of the ones that have been studied, are in the tropics. We do know, however, that all reservoirs emit some greenhouse gases, but it's not necessarily clear in a lot of cases that this is like an unnatural amount. And so what I mean by that is sometimes the dams may just shift kind of the natural greenhouse gas emissions that maybe we see in the coastal zone. They just shift them upstream because they're trapping that carbon upstream. So the whole kind of watershed emissions might be constant. The other thing that gets brought up a lot is the fact that dams also capture and bury carbon and nitrogen, which potentially offsets emissions, but there hasn't really been like a global budget done to say, how much carbon and nitrogen are buried in reservoirs compared with how much is being emitted. So that's a big kind of question mark still. And then the other thing I'll mention is all of these factors are very location and dam dependent. So I really look at these global trends, but there's very specific differences that all dams have. And so these are really kind of, I'm painting broad strokes here. So let's just go to the next slide. This is just one example from my research. So a couple of years ago, I built a model where we calculated nitrous oxide, which I mentioned is a greenhouse gas, emissions from rivers, reservoirs, and estuaries globally. And so one thing I showed in this study was that dams emit nitrous oxide more efficiently per unit surface area than other water body types. And so that suggests that even if we are kind of just bumping the emissions further upstream, the dams themselves are emitting greenhouse gases more efficiently than the estuaries would, for example. So this does sort of provide some evidence suggesting that damming may be increasing the global emissions. But again, this is very kind of spatially dependent, as you can see, just based on our relatively coarse model. Yeah, so if you go to the last slide, yeah, so thanks a lot for listening. And please feel free to get in touch with me. This was really just like a primer on some of the stuff I do and work on. And I'm really psyched to kind of keep chatting with folks if you're interested in this stuff.
Thanks very much, Taylor. We had heard a few of the kind of results of your studies, but it's really interesting to know how you got there. And I'm sure there's going to be lots of questions. So I'll look to the chat, or if anybody would like to ask Taylor a couple clarification questions before moving on, now would be the time. Could also give me a wave. All right, we have a question from Matthew. Do lake and rivers naturally emit greenhouse gas emissions?
Yep, they do. The difference is they tend to be kind of offset. So, you know, when anything kind of living in the rivers is photosynthesizing versus respiring, there'll be greenhouse gas emissions, but there'll also be sequestration. And so kind of depending on the productivity of that river and kind of how much life, I guess, is living in the river or in the lake, you'll have different amounts of emissions, maybe a net burial of emissions depending on the river. But yeah, I mean, just because we breathe and other things breathe, there's going to be greenhouse gas emissions taking place.
Great. All right, well, looking forward to hearing more from you in the discussion. So let's move on to Dr. Phillip Harrison. I'd like to welcome him. He's a research scientist at the University of New Brunswick, investigating fish passage at Mactaquac Dam on the Woolstock River in Fredericton, New Brunswick. And Phil's principal area of expertise include fish movement ecology and upstream and downstream passage at hydro faculties. So welcome, Phil, and hopefully I will have less problems with my mouse control this time. I had to shut off my ghost mouse, so welcome.
Great, well, thanks for inviting me. It's great to be here. It sounds an interesting discussion. Yeah, so I'm at the University of New Brunswick. I'm a research scientist studying the Mactaquac Dam, pictured here on the Woolstock River. I'll dive straight into the next slide if I can. So I'm just going to start off with the question: so why do fish need to move? Fish need to move to access spawning habitats, to access feeding habitats, and often to access either overwintering or summer habitats. And we often think about the need for fish to move in iconic species such as salmon, which migrate from the marine system into fresh water. But it's also, we have some fish species that do the reverse, such as eels. These guys migrate from fresh water to the marine system to spawn. But notably, it's not just fish that typically considered migratory species that require connectivity in rivers. Lots of species such as burbot, walleye, etc. also require connectivity. So fish generally need, river fish generally need three directional access, so access to upstream environments, downstream environments, and also access into the floodplain during high water periods. So yeah, I mean, when I say the ideal dam should be invisible to fish. So that is fish passage past the dam should be safe. So fish should not be injured as they go by. It should be timely, so fish are not subjected to a significant delay in their migration. And it should be effective, so that a large proportion of fish that reach the dam can pass by, i.e. effective. So yeah, we'll move on to the next slide. So hydropower dam impacts on fish upstream movements. So, and this, I'm just going to go through the impacts, assuming there's no fish passage facilities. So hydropower dams typically represent a 100% barrier to upstream movement. Fish can't swim upstream through the turbines. They typically can't swim up the spillways. So there's no access to upstream populations. So with no fish passage facilities, you would expect population collapse of fish that require upstream access to spawn. For example, the Columbia River salmon, they built a lot of dams in the Columbia River in the 60s, didn't provide fish passage, and the populations collapsed. But equally, there are a lot of freshwater species that can be impacted by dams and not being able to migrate upstream. The populations become fragmented, and this can lead to population decline. And it's important to note that the reservoir itself can also act as a barrier to fish movements. So riverine fish have difficulty navigating through reservoirs. They don't have the typical cues of flow to find their way into and out of reservoirs. And typically, they're in the reservoir upstream of a hydropower dam. You see big changes in the fish community from a more riverine species that were there prior to dam construction to a more lake-dwelling species following construction of the dam. So yeah, next slide. So hydropower dams also impact downstream passage. And so a dam without any downstream passage facilities represents like a partial barrier to downstream movement of fishes. So typically with no bypass, fish must pass through either the turbines or spillways. And on average, although it varies greatly between species and study sites, on average, fish, around 70% of individuals survive passing through the dam, so 30% die. Small fish tend to have a higher survival rate. They're less likely to get struck by the turbines. And there are certain species that seem to have a high mortality as they go down through turbines, such as eels and also big fish like sturgeon. So even the fish that survive going downstream through a dam, if there's no upstream passage facilities, they can't make it back to the upstream, so they're lost to the upstream population. And fish, the reservoir also acts as a barrier to the movement of fish downstream again. And just another impact that can occur is what we call entrainment, so that's accidental passage. So fish that are living in the reservoir may be swimming close to these turbine entrances and get sucked downstream without intending to migrate. Yeah, and you can see that's just a conceptual model in that picture here of the turbines and the spill gates. Okay, let's move to the next slide. So upstream fish passage facilities. So from a historical perspective, lots of dams were built with no upstream fish passage in the 60s and the 50s. They just built these things and didn't think of the idea that they might affect fish movements. And so a lot of dams were retrofitted with upstream fish passage facilities. These were kind of designed often designed by engineers without much knowledge of fish biology, and they kind of assumed that if you build a fish passage way, a fish ladder, etc., that the fish will automatically just swim up there. But of course, experience shows that it's actually quite difficult to design an effective upstream passage facility. I mean, there's a lot of variation in designs of upstream fish passage facilities. You can have ladders, such as this one pictured up here, which is kind of what you typically think of as a upstream passage. Then larger dams often have a kind of truck and haul facility. So they trap fish downstream and then move fish by truck to upstream locations. There's even a salmon cannon pictured here, where some It's one of these inventions where they basically pump fish upstream through a cannon, and nature-like fishways too have been designed. But it's very difficult to design an effective fish passage facility. They require an adaptive approach. So it's no good. You can't just design one of these facilities, put it in, and be done with it. Often they require a lot of changes to tweaks to make them work, and that can be very expensive. And they require considerable monitoring too, so it's quite expensive. I mean, not many fishways are particularly effective, and some of the best ones, such as on the west coast in North America, on the Columbia River system, these have been a sort of trial and error approach that's occurred over 10 or 15 years. And the bigger the dam, really, the more difficult it is to pass fish upstream. And notably, these typically were designed for a single species, usually some sort of migratory salmon, and they're not proven to be effective for other species. Different species require different flows and can climb different angles, etc. And so they're rarely effective at moving multiple species. And the state of the science is that they may be safe, they might not harm fish as they move through, but whether they're timely is debatable. There's often a delay in migration associated with these, and are they effective too is a big question. So yeah, the next slide. Downstream fish passage facility. So downstream fish passage facilities, these are much rarer than upstream fish passage facilities. Often they build an upstream ladder and then don't think about moving downstream. And there's two kind of typical ways to mitigate passage downstream. One of them is more fish-friendly turbine designs. So the turbines can be designed to reduce collisions and reduce the pressure changes that can harm fish. Although they might result in like a 2% or a 5% improvement in fish mortality. They're not going to change it from 10% to 50%. Or there's these things called downstream bypass facilities, and these work basically by attracting the fish into this facility prior to going into the turbine, and then passing them downstream, not through the turbines. Now, notably, upstream passage facilities, they designed for upstream, they don't work at all for downstream passage. Fish do not swim into them. So there has to be, these facilities have to be specifically designed for downstream passage. And working models of these are almost exclusively built for salmon smolts. There's a few that have been tested to work for eels, etc. But I don't think there's any that have been proved to be effective for multi-species passage. So that's one thing to think about. And whether they are safe, timely, and effective is still a question that needs significant amount of research. So yeah, I think that's me done. Thank you very much for having me, and of course, happy to take any questions later on in the discussion, so I didn't put my email on there, but I can share my email with you guys and stuff too. Happy to chat about some of our work here on the MITACS Dam, and thank you very much.
Thanks, Philip. That was very interesting. Are there any questions from the audience? I have one if nothing appears in the chat or I don't see any hands. Oh, there we go. Shelley has a question in the chat. Are there still salmon above the river? There used to be lots. Is this in a particular place you're thinking of, Shelley?
Shelley, you're muted.
Sorry, I didn't quite catch the. So, are we talking about MITACS Dam here, my study system, or in general, do the dams still exist?
Yeah, in your study.
There is a fish passage facility at MITACS Dam. It was built in the 1970s, and there used to be a run of approximately 20,000 salmon per year. But this year, I think we had under 300 salmon arrive at the fish passage facility. And so these guys are trapped and trucked upstream from the facility. So yeah, there are still salmon in the river, and they are still transported upstream, but very few left in that population.
Thank you. Annette asks also, are there any promising ideas on how to facilitate fish passage at MITACS?
Well, MITACS is an interesting dam in that it has a concrete aggregation problem, and so the dam is lifetime of the dam has been reduced significantly by 40 years or so. So there are questions about what is going to happen to this dam. Will it be retrofitted, or will it be removed? So obviously, if the dam was removed, then this would be the best way of facilitating fish passage at the location for sure. But in the meantime, we're doing studies on the fish passage system itself and looking at ways of optimizing passage. Some of the key aspects are providing suitable attraction flows to get salmon in, and working with the design specifically of the fishway, improving how large it is. But with such a low population of salmon, I think it would be difficult to generate effective movement of salmon upstream.
Okay, thank you for that. I think we have time for the last question from Matthew. Is there a difference between run-of-the-river dams and ones that create reservoirs in terms of fish passage ability? If you have a brief response to that.
Briefly, yeah. I mean, there can be a difference, but most run-of-the-river systems, turbine authorities, the power companies like to run the turbines, right? So there's still for downstream passage, still the majority of the flow will go through the turbines. So really, in that sense, that there isn't a great deal of difference in downstream passage success. In the upstream, it shouldn't really make too much difference to the upstream passage success. Only that typically run-of-the-river systems, they don't have the huge head heights that some of the storage reservoirs do, and it's harder to get fish up a higher head height dam, right? So yeah, that's an overview.
Thank you. That's really helpful. Thanks so much, Phil. So our next speaker is Dr. Andre Santeller, and he's a professor in hydrology at INRS in Quebec, and he's also a fellow of the Canadian Rivers Institute. So I will welcome Dr. Santeller, and just let me know if you'd like to share your screen and if you have that ability. Otherwise, the floor is yours, and I shall spotlight you.
You will need to provide me with sharing privileges. Hi, everybody.
Do you have the ability to share your screen?
I will have it if you go to security and enable it.
Okay, Shelley, also if you're here and you have the ability to do that.
Oh, well, you have to stop sharing my picture, I suppose.
Okay.
You can see from my face now, this picture was taken a long time ago. My hair.
So security.
Right.
Oh, there we go. Thanks, Shelley.
See this now?
Perfect.
Thank you for having me with you tonight. I was very pleased to be asked to give you my 2 cents worth on dams, flows, sediments, and I decided to add temperature as another interesting variable, and that is impacted by impoundments. So I speak to you from Quebec City, which is the unceded land of the Huron-Wendat Nation, and I'm a visitor that has not been thus far welcome to this area, but and I recognize that this is a fault. So we're going to be speaking about these three important variables that are being affected by dams. You've all seen the statistics about dams worldwide. This is not quite up to date, but if you were to count every small crest, large crest, broad crest, weir, and dams of all sorts in Canada, you come up with a figure that is higher than 14,000. And this is a breakdown of the large dams in Canada. This is not quite up to date, as you can see, 2003. But suffice it to say that Quebec is still the champion, followed by Ontario, BC, but Newfoundland and Labrador is right up there with 90 large dams. I'll go right into what happens when you dam a river and what happens to flow in particular. So we have different types of dams. Matthew alluded to run-of-the-river dams. Phil and explained how that may not be so much difference for fish passage. But when it comes to flow, we tend to look at dams in different categories. So those that we call storage dams, which have a large reservoir and store water for a long period, versus run-of-the-river dams, which tend to have smaller reservoirs, not much of a storage capacity, and therefore store water for a smaller period. If you're looking at large dams, the typical shift in river flows look like what you see on this graph from a study done by Ali Hassani at University of Quebec in Trois-Rivières. And what he's looking at in the top graph is the frequency of occurrence of the monthly maxima and how that is being shifted from the natural river in black versus the regulated rivers in gray. So what you can see, of course, that in a natural river in Quebec and probably in most of Newfoundland and Labrador, the peak flows occur in April and May and sometimes in June if you're higher up in the north. And that is being shifted to peak flows in the winter for most high capacity dams, because that's when we need electricity. And so that's when the turbines are running full-fledged. Conversely, if you look at minimum flows, that's the bottom graph. What you're seeing is that a natural dam would have is minimum flows occurring either in the midst of winter, so January, February, and the beginning of March. And again, some minimum flows in August and September, but in the spring, of course, you'd be running floods, so you wouldn't have minimum flows. But when you're damming the river, then the minimum flows tend to actually occur in April and May. So we're reversing the hydrological cycle in most cases. And when you look at what this means for many rivers, so Ali Hassani looked at 25 dam rivers in Quebec, and he compared the estimated natural flow, mean natural flow. So this Q50 on the top graph is the median flow, so it's the flow that occurs 50% of the time. He looked at what a natural river would be providing in mean or median flow. Those are the dots versus what the dam rivers in Quebec are providing. You can see that there's quite a dramatic difference. And in most cases, it's much lower. In the bottom graph, he's looking at the number of regulated rivers for which the estimated flow, natural flow, was significantly different, the actual flow that was measured. And you can see that for many months, it's above 50%, and in some cases, it's 100% of those rivers. So what does that do? Well, when you're looking at what it means for the biology, one of the first things that we're looking at as human beings is what happens to fish and fish habitat. And Phil alluded to the notion of connectivity. As you build a dam, you're disconnecting the upstream from the downstream. But even if you're just looking at what happens in terms of altered flows, even downstream, you are providing less water at different times. So you're disconnecting key habitats at key timings for different species. So in this figure, what you're seeing is how does disconnectivity occur? So the index is called the mean connectivity index. And you know, a low value means that the habitats and the different habitats required for different life cycles of the fish are being disconnected through damming, and the high value would mean that you have high connectivity. And of course, this has been divided in this picture, this study by Barbarossa and their friends, by looking at non-diadermous species, so the species that are strictly freshwater dwelling, versus the diadermous species, those who actually migrate to saltwater, either for spawning or migrate from saltwater to fresh river to spawn. And so what you can see, of course, is the dark values are bad. They show very low connectivity, and they tend to occur, of course, where we have most dams. So North America, South America, especially Brazil, Europe, and South Asia, with some occurrences also in Southern Australia. And there are projections to see how that might change as we are building more dams, as Roberta explained. And that's the second graph that you're seeing there. And the difference between the two is shown in the bottom graph. So you can see that if things just keep going as they are, well, we're going to lose connectivity in most parts of the world, at least for what we know where we have data to show for. The other aspect of damming that is becoming more and more in fashion is a phenomenon called hydropeaking. And this is the idea that you and I tend to all go home at the same time, all turn on the lights and the heat at the same time, and boil water at the same time. So electricity is required at peak hours far more than it is in the normal during that nighttime or during the working day time. And so the way to answer to that need is simply to push more water towards the turbine. And of course, once that's done, that water flows downstream and it provides these very peaky hydrographs. So if you're looking at the top graph here, what we're showing is how flow changed during a period of 3 days from the 23rd of August, 1999 to the 26th of August, 1999, during an experiment done to look at fish stranding downstream of the dam. And you can see that the flow rapidly go from about 35 cubic meters per second to more than double that amount in no time. And then it goes right back down to this 35 cubic meters per second minimum flow. And that's within 24 hours. So the fish have to adapt to this. And the experiment was done by using two different variables. They looked at providing essentially a water hole for fish to stay in a fish trap and see if they would stay there or they would leave, but also looking at fish that were actually stranded and dead and versus stranded and alive. And you can see that you have these three occurrences of the very low flows indicated by arrows in the top graph, and you can see what happened to the fish in the bottom graph. So many were not found, so presumably they found a place to hide, but there were in 2 occasions stranding some mortalities, and in the first occasion they tend to be hiding more in the net bag, and they didn't find a whole bunch. So mortality due to stranding can occur during hydropeaking. We're turning now to sediments. The first interesting aspect of sediments is that it's very different in dams from upstream to downstream. And of course, Taylor alluded to that because some of the nutrients are being carried down by sediments, at least the particulate matter is. And you can see what can happen downstream when you're doing hydropeaking or you're releasing large amounts of water from dams in a short period of time, and it tends to erode the riverbanks and the coast. And here's an example that would happen in a river in Laos, where you can see that big chunks of the river bands were just eroded in no time. I kind of like this picture because our buddy here was going swimming naked and somebody put a smiley face on it. So when we're looking at what happens to the physical effects of a dam in terms of sediment, of course, a dam is a big sediment trap. So it tends to keep, especially the finer sediments upstream, but it keeps, so it changes the sediment dynamics both upstream in the reservoir, of course, but also downstream, given that the finer stuff can't really escape. And thermally, as we'll see later on, of course, you're turning part of a river into a lake. And so what tends to happen is you get thermal stratification, which simply means that because water is still, there is no mixing, the top layer will be much warmer and the bottom layer will be much colder, just as in the lake. So there are many ways to move sediments, and here's how sediments are being moved around a river, a natural river. You will get the flow going from the left side of this image to the right, and you can see that if the flow is high enough and the velocity is high enough, you can get the coarse sediments to roll, the finer sediments to hop, and the finer sediments, the much finer sediments, will eventually get in suspension also at much lower velocities, but they will be stopped if there's an obstacle to a certain extent. And that's what happens in those reservoirs. You will tend to get an accumulation of river sediments, and of course organic matter settles, so you also get organic sediments, and it means that those fine sediments are not available downstream. And so you get, but you also get reduced flows in most cases, which means that the velocities downstream are much lower. And so again, it means that there will be less sediment delivery downstream and eventually into the coast. So here's an example of a study that was done by Baker and his friends, where they looked at the effects of the diversion dams on sediment and hydraulic conditions. And it's a difficult figure to really graph, but the bottom line is, if you're looking at the dark lines, it tells you where we have the aerial extent of high percentage of fines in fast flowing reaches. And the gray shows you the aerial extent of fines in slow flowing reaches. And the empty ones tell you how much pebbles you had in the area. And the take-home message from this is that in the upstream reaches, upstream of the dam, you have much greater percentage of fine sediments. Whereas, I'm sorry, there's a French sentence there. There's you go for translation. But if you're looking at the mean diameter or the diameter of the sediments that correspond to the 84% of the mean diameter, they tend to be much higher when you get higher slopes, so greater than 3%. I'll turn now to water temperature very quickly. Of course, if you have a reservoir in a dam, what you're doing is turning, as I said, part of that river into a lake. It will warm at the surface, heat up at the surface, and it'll tend to stay cool at the bottom. But most cases, when you're looking at a storage dam, you're releasing water from the bottom of the dam or near the bottom of the dam. And of course, if you're comparing these graphs, this is a graph where you're looking at time series of water temperature for only 4 days in July. And you can see the natural daily cycle of temperatures being cold at night and warm during the daytime in a normal natural river. And you can see how that cycle is depleted for a run of the river dam and further depleted for a storage dam. And if you add peaking to that, then you're really disturbing the full cycle, whereas you have only one peak of high temperature on a non-regulated river. You could get multiple peaks if you're hydropeaking at high frequency. On the right-hand side of this figure, this is work that was done by one of my PhD students, Audrey Maher, and she looked again at comparing the first plot that you see on each graph is looking at the distribution of values from unregulated rivers. Then you have a plot for run of the river. The third one is for storage. And the last one is for peaking dams, hydropeaking dams. So these graphs, these bar graphs, the way you look at them is that the center line is the median. So it's kind of the average. And then you see the boxes and the mustaches, they're really looking at the spread of the values for that specific thermal metric. So she calculated a whole bunch of different thermal metrics, looking at, for instance, of course, the mean temperature, but also max temperature, the frequency of temperatures exceeding 90 degrees, the duration of events that were above 25 degrees, frequency of events higher than 25 degrees C. And the take-home message, again, without going into the details, is that none of these metrics, whichever you looked at, remain the same between a regulated and a non-regulated river. And really, run-of-the-river dams tend to be not so harsh on the temperature regime, but as soon as you have a storage capacity or you're peaking, then your entire thermal regime is completely changed. Of course, you can remove dams, and this is something that's being done. I just want to finish quickly on this. Is when you look at dam removal, it's certainly happening in Taylor's country more so than in Canada. We can certainly think that things are going to come back to normal in one day, and that was one of the scenarios that was looked at in the project that Phillip is working on the MITACS River, whether a dam removal would be a solution. But we know that if we do that at one point, there will be a period where the ecosystem is not going to be very happy, simply because things are moving around. Sediments will start moving again around. The thermal regime will be disrupted again. And so for this reason, it takes a while before the ecosystem might recover. But in the States, they took that bet in many instances, and you can see here the number of dams that were removed in the US. So here you have on the first figure the total number of dams prior to removal. You see where dams were being removed. So greater than 75 dams were being removed, 95 in California. And you can see that most of the dam removal happens in the northeast of the United States. And that may be something that's coming our way. The science is moving towards that. We are doing better at modeling those conditions. And it perhaps is a message of hope for certain of us. And with this, I'd like to thank you and be happy to entertain questions.
That was great. Thank you so much for that talk. We'll look to the chat for any questions. We have something from Roger here. So, are high winter flows a requirement for subarctic and Arctic rivers so that there's no freeze up at the dam?
So thank you for this question. So typically, of course, as we said, those high flows do occur in the winter simply because that's when we want to have electricity. Most of the dams are used for hydro. And so that would not be the case, for instance, in the southern US, where they might be using more electricity in the summer because they want to have air conditioning. But in our case, that's what tends to happen, which means that a lot of the reaches right downstream of the dam stay ice-free for long periods during the winter. It also means that we're releasing water that is at a temperature higher than zero into the system. And that has a lot of disruptive effect to, for instance, the fish that may spawn in those rivers. We're looking in Phil's project at AMES, we're looking at what might happen to the fish spawning downstream of some of the dams upstream of MITACS and how that they may be affected, because salmon, as you've heard, do go up there and they're being confronted with temperatures that are higher than normal, which means that the juveniles will come out of the eggs earlier than expected, and they may be confronted with adverse conditions. What might that do to the downstream, further downstream to the coast, has yet to be really studied in details, but we can expect that delivering warmer water in greater quantities in estuaries, for instance, would have a great impact on the mixing of the fresh and the salt water downstream.
Thank you, Roger. We have another comment from Annette. Also, the flows are adjusted in the fall during freeze up to establish a high ice level to all water to pass underneath to the turbine intakes.
That's a very good point indeed. Yeah, so we're tweaking these flows to make sure that there's no ice that's going to damage those turbines intakes, and so of course we're disrupting the flow pattern even during the freeze-up phase.
That's great. I'm seeing a lot of great opportunities for intersecting conversations with everyone. If there's no other questions for Dr. Santeller at this time, I would invite everyone to maybe take just a couple-minute bio break before we go to our last two presenters and then on to our discussion. So just 1-2 minutes while I essentially figure out how to get my screen back on. So take a stretch, go get a glass of water, take a walk around for a second, and I'll be back in just a couple minutes. Thank you. All right, we'll wait to see cameras turned on. Sometimes it's nice just to have a few seconds to reset.
Sandra, are you handy? Are you near?
I am.
I'm just thinking that if we could ask each one of the presenters to put their mailing address in the chat. Can we capture the chat?
Yes, we will have a record of the chat.
Okay, because I think I would mail each one of them a copy of the Arctic Blue Deserts, Steve Kasperzak's new book, if I had their addresses.
I also have their contacts, so maybe that's something we can connect with them by email so that they're not sharing their information publicly, but I'm happy to coordinate that. That's a good idea.
Yes, that makes sense. Okay, great.
Perfect. So I'd like to welcome everyone to make their way back. And when you're back, if you can just turn your screens on so we know when to start. Thank you. Perfect. Any action in the chat? All right, great. Thanks, Shelley. Perfect. So I'm really pleased to continue our great conversation now and invite Dr. Annette Luderman, an independent ecologist who did some research on the effects of dams on riparian habitats. And this was in the Churchill River, and she currently works with several Indigenous nations in Canada, in northern Manitoba, Saskatchewan, and British Columbia, assessing the impacts of dams and their operations on riverine habitats. So really excited to, we've had fish, we've had diatom, we've had flows and sediments. So now let's talk about some habitats. So thank you very much.
Hi, everyone, and thanks very much for inviting me. Yeah, I'm delighted to actually reconnect with Roberta and other folks in Labrador, having spent a lot of time there when I was working on my doctoral research. First, I'm speaking from Golden on the Columbia River in British Columbia, and this is within the unceded territory of the Ktunaxa, the Secwepemc, and the Métis Nation Columbia River Society. I'm fortunate to be living in the upper part of the Columbia, which does not have any dams on it. And the wetland and riverine environment here is incredibly rich and diverse. I have opportunity to explore it frequently and work with students here as well. It's an absolute pleasure, and it having spent time on the Churchill River, Mishishibu, with Innu and Métis co-researchers, it breaks my heart really to be watching, I guess, from this perspective on the other side of the country, what has happened to the lower part of the river since I've been there. I'm going to just briefly make a few points about some of the observations that we made on the Churchill River, looking at riparian habitats. And I want to say, being introduced as an expert, so much of my expertise has come from working with Indigenous peoples on the land, from spending time paddling a canoe, observing for as much time as I can. And working on environmental assessments, you really see how when we assess a proposal for a new dam, we see the conclusions often about environmental impacts are that the impacts are not significant. And of course, one of the reasons they come to these conclusions is because the research that's done is very short term. We're not considering whole ecosystems. We are struggling with getting our heads around cumulative impacts. These systems are incredibly complex, and the impacts that occur due to building dams and operating the dams are very long term, as we've seen from some of the presentations that have already been done. And there's so many more elements to the ecosystems that we haven't even begun to touch on. So I'm going to just talk briefly about what we observed in the Churchill River, the changes in riparian habitats due to flow regulation. And riparian, we're talking about this whole area in between the aquatic environment, the upland terrestrial environment, which is influenced by the seasonal floods that occur in a natural system, and are influenced by in a boreal system like this, by the weather patterns and the climate. So the freezing during the winter time holds the ice in place in most places, and has a big effect on whether or not the vegetation on the shorelines is able to actually survive and thrive. And so we're looking at the systems that have co-evolved with all of the physical, chemical, biological components interacting with one another. And we're also looking at systems that are intricately connected to marine systems. We often in environmental assessments, people try to separate it out. We'll look at the marine and we'll look at the freshwater, but obviously, as everybody here recognizes, these are interconnected and cannot be understood in a kind of a short-term fragmented way. So here's the Churchill River. The gray line looks basically shows part of the watershed, so all the water within the area that's flowing into the main stem of the Churchill River. And as I think Dr. Hilaire pointed out, the effects that you see on riparian habitats and wetland habitats are very much dependent on the way that the dams are operated, whether it's in a reservoir like the upstream part, these huge reservoirs, Smallwood, Osakmanuan, or whether they are diverted reaches. So the yellow lines show Naskapi, Kanyartok, parts of Twin Falls and so on, where those rivers were diked, and so they have a reduced flow. The seasonal flows aren't so much affected, but they have reduced flow from pre-dam conditions. And then the green areas show downstream effects. And we have a dam up in the upper left-hand. The Menehek Dam also has downstream effects there, which in an area which was a part of the Churchill watershed as well. So it's quite a complex system. And I'm just going to show you a few examples of what we observed in these different parts of the hydroelectric system before the Muskrat Falls Dam was built. So it's effects from the Churchill Falls Dam, which you can see the left-hand red dot there, and just significant long-term effects that we could see on the riparian habitats. Next slide. Yeah, so these, when we talk about riparian, again, I say anything that's connected to the river, which is influenced maybe on a year-to-year basis, and sometimes on a 20-year cycle or a 50-year cycle of extreme floods. So when you have in the left-hand picture here in Lower Brook, which is now within the Muskrat Falls Reservoir, you see these oxbows, very complex combination of different types of vegetation, structurally and species rich. These areas are created by those natural seasonal patterns of flow. So the water coming up into the low areas and bringing nutrient rich sediments and plant seeds and plant propagules. So bits and pieces of willows and so on that will take root when they're in good conditions. And so this provides a really diverse habitat for all kinds of species, terrestrial and aquatic species, fish nursery areas. And then we can also see how the sedimentation in a natural river will create kind of a shifting pattern of areas where the sediment is building up and areas where it's scouring away naturally. So over time, you get what they often people call a shifting mosaic of these early successional habitats. And this is partly what makes the river system so biologically rich and diverse. Our next slide, we don't have a lot of time, I guess. And so the types of impacts you see on riparian habitats from dams are obviously, some of them are permanent in the areas where the dams themselves are built, or in this case, the Churchill Falls project created 113 kilometers of dikes. In these areas, for the most part, a lot of times they're basically stripped of organics too, so they're you don't have a good substrate for shoreline vegetation to develop, but also mainly because of the hydrological changes, you don't see good development of riparian vegetation. So these places are very species poor, don't provide good habitat for many aquatic or terrestrial species. And I just throw in this conceptual image of Muskrat Falls on the upper right there. we talk about our dams green. I think they progressed a little bit from a few years ago when they first started putting out the conceptual images of what they wanted to build the Gull Island Dam, and they actually painted, they actually made the dam actually green in the picture. This was for marketing purposes, obviously public relations and so on. And I think we can see that there's not a lot of green growing on these dams in general. Next slide, please. And so this shows 2 years. Just want to get a sense of some of the specific changes that happened in the flow on the Churchill River due to the Churchill Falls facilities. So here we see 2 years of data from Flower Lake in the late 1960s. So the red line shows the flow patterns that occurred before that suite of facilities was built. And so you can see in the wintertime, as Dr. Hilaire pointed out, the flows are very low in the wintertime. And then you have a peak in the spring with the spring freshet and the snow melt. And then through the growing season, June, July, August, the water levels are coming down. And so during that time, the aquatic plants, the sedges that are growing up out of the water, the herbs and shrubs on the higher levels of the banks are all able to grow. And then what we see with the flow from the powerhouses, and these are data from 2000, 2001, but things haven't changed, right? Because generally they're operating these facilities to maximize hydroelectric power, not to try to balance ecosystem effects. So in the wintertime, you see very high flows. I guess you can't see my cursor anyway, so but you can see it's basically the opposite type of pattern plus a lot more variation. And so if you do get a lot of variation during the wintertime with high flows, you're also going to have effects on the shoreline, which in most cases increases erosion over natural erosion processes and increases ice scour. And so there's a whole suite of effects on the riparian habitats that are caused by that, as well as the more frequent daily fluctuations of peaking reservoirs in the summertime during open water. Next slide, please. Try to get through. So this shows the water levels in the Smallwood Reservoir for a number of select years. And what I just wanted to point out here is that, so it's a storage reservoir. They store the water during the spring freshet and the summertime. So you can see how at the left of the graph in the wintertime, the water levels are being drawn down. And they talk about a drawdown zone of about 4 meters. But in fact, if you look at high water years and low water years and put that collectively together over a period of a couple of decades or so, the drawdown is actually more like 8 meters or more. And then you see how the water levels go up in May and June, and they continue to go up. And so any plants that are trying to establish on the shoreline mostly don't have a chance because they are not experiencing the kind of hydrological conditions that they have evolved with. Next slide, please. Yeah. So here's just a little diagram that shows you the top in a natural regime. If you have good conditions, obviously, if you have bedrock or very steep slopes that are boulders and larger rocks and so on, without a lot of sediment deposition, then you're going to have a different type of habitat that establishes in that particular place. So the upper diagram though shows a marsh-like habitat where you have aquatic vegetation growing under the water where it gets enough light, it's shallow enough, not too deep, and then emergent vegetation, again, the herbs and the shrubs, and so you get this complex of vegetation. And in the middle, what we saw in Osakmanuan in Smallwood Reservoir, and in all the major storage reservoirs I've seen all across the Canadian North, and what they've seen in Sweden and in boreal environments, these storage reservoirs don't tend to grow very much vegetation at all. And the drawdowns, and this is very large areas in the drawdown zone. And then control reservoirs with a smaller fluctuation have a very narrow riparian zone, so not a lot of diverse habitat there. And this is often the case in run-of-river peaking reservoirs that have a narrow fluctuation. Next slide, please. I'll try to finish off here. So these are some pictures that show you the consequences of the operations and the changes in the flow regimes in the Smallwood Reservoir and Osakmanwan in the top. And what I really want us to think about is the magnitude, geographical magnitude of these types of effects that we see not only in Labrador, but in Quebec, of course, northern Manitoba and Saskatchewan, British Columbia, all over the Canadian North in these very large mega projects. We have these huge areas that are essentially very much degraded riparian habitat. And so Osakmanwan has a perimeter of 751 kilometers. And that's just a kind of a coarse view of the actual shoreline habitat that's affected. And Smallwood Reservoir, over 3,000 linear kilometers of shoreline that are subjected to these huge drawdowns. Next slide, please. And this is just to show you the type of riparian habitat you see in these forebay reservoirs, where very narrow fluctuations, which is often argued by proponents that it's a good thing when we stabilize the water levels. And it's actually not a good thing at all in ecological systems that are adapted to a dynamic flow, but only according to the season. Next slide, please. Almost done. And this is just an example of some of the lower Churchill, so below Churchill Falls. We saw lots of increased erosion due to the higher winter flows and the daily fluctuations. A lot of ice scour and increased erosion and ice scouring along the banks, but we didn't have data from prior to Churchill Falls about rates of erosion. And so it's easy for proponents to try to argue that we can't really say if erosion has increased, but it's clear that it has, and it does in all dams because of sediment capture behind the dams, like as other speakers have said. And I think, Horace Gowdy, he was a trapper, he said most of his life on the Churchill River trapping, his younger life. He said he didn't have any electricity, and it was a mighty damn good life, he said. And when he looked at these pictures, he said that the beavers used to be able to create lodges and their little dams at the tributaries and create a lot of habitat diversity all up and down the Churchill River and up into Mishikamau, where Smallwood Reservoir is now. And he said they couldn't do that after Churchill Falls. They just gave up. He said they had to pack that in. And this is something which is the case for aquatic mammals through very, very large areas of these mega projects. Next slide, please. Almost done. And so this just shows you the Labrador and Gava Peninsula and the major watersheds that are affected by suites of storage reservoirs, forebays, controlled reservoirs, run-of-river, and downstream effects. And the effects on the marine environment from these major projects, and as earlier speaker looking at the global effects of these is absolutely, there needs to be a recognition of the significance of what we're doing and the scale of what we're doing in terms of changing these ecosystems. So last one. Yeah. And I think that the understanding of the impacts of these dams, it can't be obviously just looking at the physical impacts. It's a very deeply significant to people who know these landscapes intimately and then see them changed forever, unless maybe we take the dams down. Obviously, very, very long-term impacts and culturally devastating for many people. Thank you.
Thank you so much for that, Annette. And you finished exactly where I like is kind of reaching to those social, cultural dimensions that we talked about in the first knowledge sharing session. And we've heard a lot of natural science up to this point. So just before we move on to Dr. Nick Mercer, any quick clarification questions for Dr. Luderman? Or please feel free to save them for after we hear from Nick and we can discuss it as a panel. All right, perfect. So I will like to, oh, it stole my, nope, there we go. So I'd like to now welcome Dr. Nick Mercer. Thanks for sticking with us. We really wanted to provide as many perspectives as possible and are so happy to have him join us today. He's going to let us know what he's been up to as it relates to more local participation around energy projects, social cultural dimensions, and distribution of benefits. So thank you very much, Nick, and I will leave it to you and I will pin you to the floor.
Excellent, perfect. Hi folks, my name is Nick Mercer. I'm a settler researcher. I completed my PhD in geography environmental management at the University of Waterloo back in 2020. I've had the great privilege for about the last year and a half to the regional energy coordinator for the Nunavut government based out of first Happy Valley Goose Bay, but then Nain in Labrador. I, however, since have returned to the Ivory Tower and I'm working as a postdoctoral research scholar within Dalhousie University School for Resource and Environmental Studies. So of the panelists tonight, I think I'm the only social scientist. So I think I have some large shoes here to fill. But I think this is a good place to end the discussion tonight. So I'm going to be talking a little bit about community ownership and control over renewable energy projects and present a model that I developed in partnership with the Nunavut Community Council, which we're hoping will help to confront some of the tensions of a mega energy development in Labrador. So you slip to the next slide there. A couple clicks there. So I guess everybody at this point knows that Newfoundland and Labrador is normally held up as a global leader in renewable energy development, and much of that's attributed to the fact that the province currently gets about 94% of its electricity from mega hydro. So when and if Muskrat Falls is completed, that figure is expected to rise to 98%, which everyone really loves to celebrate. But as a geographer, I love questions of scale. And if you zoom in a little bit, there's places where the electricity generation mix differs really dramatically. So across the coast of Labrador and Newfoundland, there's 20 isolated communities not connected to the provincial electricity grid that remain almost exclusively dependent on diesel fuel for electricity generation. And combined, these communities are consuming in excess of 20 million liters of diesel fuel every single year. And I think one thing that's imperative to point out about this map is that the overwhelming majority of these communities are Indigenous communities. So in Northern Labrador, of course, represented by Nunavut government, Innu Nation and the community of Notwashish, and then of course the Nunavut Community Council in Southeast and Southern Labrador. So just one thing I like to say when I give these presentations is that off-grid energy research, off-grid energy policy, off-grid energy advocacy, everything that we're doing here today must be centered on the rights of Indigenous peoples. So you can slip to the next slide there. I mean, why does anyone care? Why do I spend so much time reading about this stuff? And in general, these diesel generators pose really substantial economic, environmental, social challenges for remote and isolated communities. And I don't want to get too deep into this, but I'll offer a couple examples. So From an economic perspective, these diesel generators are really expensive. The average Canadian consumer pays anywhere from 7 to 17 cents a kilowatt hour for electricity, where the average unsubsidized cost of diesel generation in an off-grid community is $1.30 per kilowatt hour. So over 10 to 20 times more expensive. These diesel generators also pose a massive risk of fuel spills and leaks. So the government of Canada tells us that there's over 2,000 contaminated sites at or near Indigenous communities in Canada that they've counted. And the vast majority of these sites, about 70%, are contaminated by, if we're a live audience, I'd get you guys to guess, but the answer is diesel fuel. And even social issues, noise, these diesel generators can be loud, noisy, disruptive, especially in quiet, isolated northern environments. So you can go to the next slide. Now, conversely, and I'll do the air quotes, clean energy projects, sustainable energy projects, these things are frequently promoted to improve the sustainability of off-grid communities, your wind, your solar, hydroelectricity. You know, they're promoted to lessen costs, lessen subsidies, lessen the risk of fuel spills and leaks, to improve the autonomy of Indigenous communities. But here's where I want to be incredibly careful, as my research and the researcher of several others indicates that in the absence of legitimate processes of community ownership, community control, community engagement, that these clean energy projects can create very real economic, environmental, and social tensions of their own. And I'll offer a few from the social dimension, because we've done so well talking about the natural impacts of projects today. But the first, and I think this is often overlooked, is that many times these projects simply are not compatible with the needs of communities that they supposedly serve. So the government I work for, Nunatsiavut government, back in 2017, they published an energy security strategy. And what the energy security strategy found was that the greatest energy related challenge in the region was heat insecurity, or what they defined at the time as access to clean, affordable, and reliable heat. They found that upwards of 60% of their community members were living in inadequately heated homes, cold homes. And of course, over a prolonged period, a cold home can lead to an adverse array of social and mental health effects. They also found in the research that the vast majority of community members, 60%, 70%, 80% beyond, were using wood as their primary source of heat. So if someone comes in and builds a big wind farm or a solar array or run-of-the-river hydroelectric facility that's capable of providing electric heat, this does almost nothing to improve the most pressing energy-related need in the community, which is access to clean, affordable, and reliable heat. So example number one. Example number two, I find this one really funny. Self-determination or self-sufficiency. You know, these projects are promoted to improve the self-sufficiency of communities in three ways. Number one, by producing your own energy, you then don't have to import it from elsewhere, so you're less reliant on imports. Number two, by owning these types of projects, you know, you can facilitate processes of self-decision making. And number three, by selling electricity, you can generate a bit of money that you can then invest in your own self-determined priorities. But what the research is showing is that these projects can actually infringe and erode self-sufficiency in three ways. Firstly, far too often it's not communities themselves that own these projects. Instead, it's outside governments, it's outside corporations. And if this is the case, this can lead to further intrusion of Western models of resource governance into Indigenous communities. So one thing I always love to ask people is Black Tickle Labrador any better off if Walmart Canada owns a wind turbine in their community and then exports all the profit to somewhere in the South? I don't think so. Number two, these projects can create massive administrative burdens for communities that are already operating at capacity. And number three, these projects, as folks in Labrador would know, can unfairly expose community members to the risks associated with novel or even pre-existing technology. So we can jump to the next slide there. And once more. So, I mean, the question that I love to ask is, does this mean that we shouldn't pursue renewable energy projects? And no, that's certainly not what I'm arguing. But to have successful renewable energy projects, then they must be embedded and legitimate processes of Indigenous ownership, Indigenous control, and Indigenous engagement. And working with two Inuit scholars, Dr. Debbie Martin, whose people come from St. Louis, Fox Harbor, Labrador, and Dr. Amy Hudson from Black Tickle, Labrador. We put this together. And I had a prof tell me one time that having a good acronym is 90% of the battle. So we called it the 4 Right Community Energy Planning Framework. And essentially what we argued is that to have successful energy projects and energy planning, our research needs to be grounded in the principles of respect, reciprocity, relationships, and rights. So by respect, we simply mean honoring all life forms and the histories and cultures, traditions of communities and energy-related decisions. By reciprocity, we refer to the notion that far too often it's just the researcher, the engineer, the manager that benefits from these types of projects and research. And we argue that relationship needs to be inverse, and it's communities that need to benefit principally. By relationships, we refer to the notion that this type of work should be considered a lifelong relationship, and that will continue to support communities long after the formal completion of our projects. And this final one is so important, right? Indigenous communities and communities in Labrador they're not another stakeholder to be consulted. I loathe that word, stakeholder, but they're full-fledged rights holders that must be respected. So the second stage of our framework, we argued that, of course, a project should never go ahead without the free, prior, and informed consent of the communities that we seek to serve. The next 2 stages kind of went hand in hand: generation side sustainable energy projects. These are your wind, your solar, your tides. But we know that these variable sources are really only capable of supplying 10 to 20% of electricity in an isolated community right now. And this is unfortunate because it's at the household level, in the way we heat our homes, use electricity in our homes, heat the water in our homes. It's here we can cut into 10, 20, 30, 40, or 50% of the diesel that we consume. So finally, we offered this idea of transition. And here we simply argued that it's only when we can maintain those principles of respect, reciprocity, relationships, rights, seek and maintain the free, prior, and informed consent of the communities that we're serving, assess the social and economic feasibility of supply side and end use energy technologies. It's only at that point where decision makers should be making recommendations about which type of technologies are going to support a community and achieving a sustainable energy future. So again, when I'm live, I love to ask people, does anyone think the Muskrat Falls Hydroelectric project would have passed through the 4 Right Community Energy Planning Framework? So I got 1 slide left there. I wanted to thank everybody for your time. Again, it's a question of scale in Newfoundland and Labrador. We're doing really good with the mega hydro on the grid, and then we're doing a really dreadful job, and there's massive energy inequities off the grid. And these projects can appear very benign on the surface of things, but when you kind of peel back the onion, if Indigenous ownership and control isn't there, they can create very real tensions. So I'll leave you with the principles of respect, reciprocity, relationships, and rights, and in the hopes that we can work towards truly just and equitable renewable energy systems. Thank you, Nekami.
Thank you very much, Nick. That was fantastic. A great way to end and kind of wrap up, summarize those social cultural dimensions that are elusive in the literature. So thank you very much. Are there any questions for Nick before we jump in to a couple questions for our panel? I recognize it's getting close to the end of our time, but really happy that we were able to maximize time with these experts to share their knowledge with you. So any questions for Nick at this point? I know I definitely have one. So maybe I'll just start there, and you guys can get ready for some panel questions. So I'm interested if you've thought at what type, and again, this could be relevant for anyone who was on the panel. If you've thought about, Nick, what would ensure that this framework or these legitimate processes are considered by proponents in communities, by governments? Is it a policy answer? Have you thought about this? Give us some
Yeah, I've thought about it a lot, and myself and tons of incredible people on this call. I see Dan Burton and Roberta Benefield have all been on the front lines for this for years, trying to center the rights of Indigenous peoples and all the decisions that we make. But dreadful things still consider to happen. There's this real, I guess, attitude and tendency out there that engineers and professionals and politicians know best, and that the solutions that they've always kind of relied upon are what will advance sustainability in the communities. That's how we got caught in this large hydro mess. But even the federal government, they recently announced a project, hundreds of millions of dollars, called the Indigenous Off Diesel Initiative. And it's like, on the surface of things, that seems pretty benign. But when you dig deeper into the framing of that program, they're already eroding the rights of communities in the way that they're framing the issues. They're telling communities they need to get off of diesel generators. How? Are you proposing we build mega dams and interconnect all the communities? Are you proposing forcible resettlement of all these communities along the Labrador coast? It's not up to you to decide how to consider or frame or address this problem. So to me, it always comes back to centering the rights of communities, necessitating free, prior, and informed consent. I know that the United Nations Declaration on the Rights of Indigenous Peoples isn't perfect. I've read some really healthy criticisms of it, but striving for provincial laws that are harmonized with UNDRIP would be a very good first step, in my opinion.
Thanks for that response. And we have a question from Matt in the chat. Have you seen any examples of megadam projects led by Indigenous communities?
I don't necessarily know led by. So there's this term, Indigenous clean energy projects, that's really gaining momentum right now across the country. But again, if you look into what constitutes an Indigenous clean energy project and who's behind it and how it's being governed, it's not what originally meets the eye. So a paper was recently published at the University of Victoria that suggested there's 824 Indigenous clean energy projects in Canada that are affiliated with Indigenous peoples in some way, shape, or form. But again, when you dig deeper, less than 24% of those actually have majority equity ownership by Indigenous people. So a 50% or greater stake or plus. And in that database, they even include the Muskrat Falls project as an Indigenous clean energy project because it has an impact benefits agreement signed with the Innu Nation, and that constitutes it as a Indigenous clean energy project. So Matthew, thank you for your thoughtful question. I can't point towards a specific mega dam, but I would suggest that when you hear a project is led by Indigenous peoples, you have to take it with a grain of salt and really dig deep into who's running the project and who's benefiting from the project.
This is Tracy Doherty. I'm in Saskatchewan right now. I'm a Nunatsiavamukto originally. I was wondering, as you said, you're in the ivory tower now. Are you seeing more? Do you think it's reaching a tipping point at all, that more people are listening to the type of knowledge that you're talking about, that we need to rebalance the power for the communities? And I'm familiar, like with Amy Hudson's work. I mean, although we have our divisions, of course, between our different Indigenous nations in Labrador, I have to say that Nunatuavut is really at the cutting edge of so much, as far as, like Amy's papers on reclaiming Inuit governance and really looking at sustainable energy. So I'm just curious if you're, I don't know, I'm such a more intuitive person, but do you sense, like, when you speak to different organizations, that we're reaching a tipping point where people are going to listen? Because I mean, we certainly had the evidence way back when. The panels all knew that there was going to be so much environmental impact, and yet they favored the supposed economic benefits over the environment. Just curious how you're feeling, I guess, about that. Are you seeing us getting any closer, like different organizations, business? Are people out there listening beyond us, the advocacy advocates for all this?
I think that's such an important question. I wish I had a really optimistic answer for you. Where I'm sensing a tipping point is with organizations like Grand Riverkeeper and at the grassroots level, who are really being heard and showing up and working hard to center these principles. Like 10 years ago, when I started doing this type of research, I was not meeting with 20 like-minded people at 9 o'clock Newfoundland time on a Wednesday evening to talk about the principles of community-based development and renewable energy and the impacts of hydro dams. So I really draw a lot of strength and motivation from that. But I'll also point towards the leadership of Indigenous communities in Labrador themselves. So Nunatsiavut government is advancing the Nain Wind Microgrid project. When it's done, it'll be the largest wind energy system across Inuit Nunangat. It'll displace over 1 million liters of diesel fuel annually, and it'll generate hundreds of thousands of dollars on an annual basis to be invested in community priorities. And that's Nunatsiavut government themselves, not Nalcor, not Newfoundland and Labrador Hydro, not some corporation from the island leading that work. Another really incredible project that they're leading is their high efficiency wood stove replacement program, where they're supporting 200 low-income dwellings over the next 2 years, transitioning from a 50-year-old clunker of a steel wood stove to an EPA certified high efficiency wood stove. And that project's going to cut back another 1 million liters of diesel fuel a year. And what I love about this project so much is it's not a mega dam. It's not this massive project that creates 5,000 jobs and then disappears 5 years later. It's intended to make a difference in the lives of Inuit and a difference in the lives at the individual household scale. So the groups like this really motivate me, and the leaderships of communities themselves in Labrador is really emerged in the last few years.
Thank you for your question, Tracy. So I just want to acknowledge that, yes, it is it is 9 o'clock Newfoundland time on a Wednesday. And I would love to welcome you to stay for another, 5 or so minutes. I'm going to essentially ask the panelists if they have any thoughts on the other presentations, and specifically because we're moving into the third knowledge sharing session in this phase of the research project, trying to understand more social, cultural, coastal and marine impacts on livelihoods, fisheries. So yeah, any general comments from any of the panelists at this point on the other presentations, or what social impacts they really see, the dimensions of their work. Maybe they don't look at it directly, but after seeing from multiple perspectives, we know that these complex problems can't be solved from just one discipline. So yeah, just open the floor for panelists to have any last words at this time.
I guess for me, I mean, I've just been sort of musing this last couple hours about like Nick mentioned being in the ivory tower, and that's like something that I feel like I've struggled with so much, is like I've spent so long in science, and I write these proposals and things, and I feel like this is honestly like one of the very first times where I've engaged with folks who really want to hear the science that I've been doing. And I guess like one question is like, can I just keep coming to these meetings and just like listening to you folks? And I think like from the standpoint of like me continuing to do science, just, there were so many new perspectives here that I hadn't necessarily considered. This is super valuable for me also, and being able to kind of start from a different place when I'm pursuing research in the future. So I guess I just want to say thanks a lot for inviting me and for listening, and for letting me listen.
Thanks for that reflection, Taylor. Any other comments from the panelists?
Zanette here. Yeah, I guess I'm glad to see people feeling motivated and positive and wanting to share our knowledge across, disciplines as experts, but as, so-called experts, I refer to myself, but with all of the people who are affected by these centralized energy, and essentially what they are, major capitalistic projects, right, that make a lot of people a lot of money and have big impacts on a lot of other people. My PhD was interdisciplinary, and I started out years ago studying anthropology and working with Quebec and Cree and Inuit on the megadams there, and realized that I needed to understand the biology, the ecology, the science, the formal science better in order to have my voice heard on what I saw were some of the problems, right? And so I think it's extremely important that we, try to avoid putting science at the forefront of our decision making, because there's so much more to learn, and to learn from everybody with different backgrounds and different types of empirical knowledge and spiritual and social connection to these places that we're affecting.
I think, Sandra, maybe the last comment I would have, I've always long struggled with the word expert, especially to wear it myself. And I've got a colleague, a Mi'kmaq colleague, Nicole Blinn from Shabuktuk, Nova Scotia, who always says that community members are the real PhDs. And I know Dan Burden will laugh at this story, but the first night I ever worked in Port Hope Simpson in Labrador, it was minus 40 degrees Celsius out. In the dead of February, my furnace went out, and I had to call the diesel plant operator to come over and fix my furnace. And he was shocked. He said, "You've been studying energy for 10 to 15 years and you don't know how to fix an oil furnace?" So community members are the true PhDs, but just a thought coming to me as we clue up. One time a mentor really told me that our role as settlers on this part of Turtle Island at the end of the day is to get out of the way and to support and amplify community members in whatever way we're asked. So I'm really grateful to Grand Riverkeeper for bringing us all together, for letting me share my 2 cents. And I'm here to help you folks in any way I can.
That's great. Thank you. And I definitely agree. Our next session is all about local experts and hearing their stories. And I know we are going to take a couple questions if anybody as a participant wants to ask a couple questions, but recognizing that we're over time, I'm just going to put up my email. And this session was, so valuable, more so than I possibly could have imagined. And I think that's why we ran a bit late. So any participants, please put questions in the chat. But I think what I'm going to do is, if you would send me questions to this email here, seager@un.ca, or in the chat, I'm going to coordinate a document and send it around to our guests today with your questions, and just make it live and share it with everyone who attended today, so we can keep the conversation going and address those questions from both the community and our panelists' perspective today. So I'll be sending that out. So is there any burning questions at the moment, or is that an okay idea for moving forward? Okay, everyone's tired.
Sounds like a good idea.
Absolutely, perfect. So unfortunately, we didn't get as much of a panel discussion, but maybe we'll be able to twist some arms and just have a group discussion in another session. So if you have to leave, please do so. I'll watch the chat for a couple more minutes. But yeah, thank you so much for joining us.
Thanks to all of you for all of your work. It's amazing.
Great. All right, thank you so much for sticking around, all of our panelists. That was great. Please, Matthew, send some questions later. That's great. I'll also send around the link for knowledge sharing session 3. Right. Any comments or thoughts as we kind of close up from Roberta or Karen? Any thoughts just for me, for anyone who's still on the line? Any next steps that you see that you'd like us to move forward with?